All right, welcome to Physics 105, Chapter 5. So we'll apply Newton's laws. So everything we've learned up to this point we're going to use. All right, we're going to draw and make effective use of free body diagrams. So now we're going to use these things that we learned how to draw. Recognize and solve simple equilibrium problems. Distinguish between mass, weight, and apparent weight. We're going to finally talk about friction and also drag. Drag is air resistance. Apply the full strategy for force and motion problems to problems in single particle dynamics. And then understand how to apply Newton's laws for interacting objects. So there's a lot to this chapter. Okay. Here's a question. So pause your video and figure it out. And I'll give you a hint. There's more than one correct answer. All right, so an object is in equilibrium. Well, what does that mean? Equilibrium just means that the sum of the forces equals 0. Well, that means that MA equals 0. That means that M delta V over delta T equals 0. So there's no change in velocity. There's no change in velocity. So that means the object may be at rest or it may be moving. We don't know. But the important thing is that the velocity is not changing. So if it's at rest, we call it static equilibrium. If it's moving, it's kinetic. So kinetic means moving, static means not moving. That's all. But basically, this is the important thing. Equilibrium means that the sum of the forces are equal to 0. So the acceleration is equal to 0, so the change in velocity over the change in time is equal to 0. All right, so we're going to be solving equilibrium problems. How do you do that? Well, that's how you do it, right? But there's more to it. What was that? All right. All right, so equilibrium means the sum of the forces equals 0, but this is a vector. So just like we learned with our, when we had vectors that were not along the x or y axis, what did we do? We resolved them. So the same thing here. So this is true, but what we're going to do in practice is we're going to say that the sum of the x forces equals 0 and the sum of the y forces equals 0. So there's really not a whole lot that's new. All right, so that's equilibrium. So what do you suppose non-equilibrium is? Well, I'm sure you can figure it out. So if this is equilibrium, non-equilibrium just means that the sum of the forces equals ma. No kidding, right? Newton's second law. And so how do we solve these problems? Well, same thing. You just resolve into x and y components. So you'll have the sum of the x forces equals ma sub x, and the sum of the y forces equals ma sub y. That's all. All right, so let's do an example. Okay, a 100-kilogram block hangs on a rope. Find the tension in the rope if the block is stationary. So how you're always going to approach these problems, you'll draw the force diagram, and then you're going to use Newton's laws to solve the problem. So 2 steps. Force diagram, which you learned how to do last chapter, and then F equals ma, or if it's equilibrium, sum of the forces equals 0. So let's do it. All right. Let's draw the force diagram. So we'll just use a regular coordinate system. And here's the object. What are the forces acting on the object? Well, there's the weight, which equals mg, and then there's the tension. That's it. Okay, so you draw the force diagram. Now there's really 3 steps, sorry. Second step, you want to ask yourself, is it an equilibrium problem or is it a non-equilibrium problem? I mean, that's the crucial question. Because if it's equilibrium, sum of the forces are 0. If it's not equilibrium, sum of the forces equals ma. So you have to figure that out. And, you know, just like I said earlier, you always want to look at the important words in the question. So here's an important word, right? Stationary. So if it were me, if this were test or something, I'd circle that word, stationary. All right, so the block is stationary. That means it's not accelerating. That means that it's equilibrium. The sum of the forces equals 0. All right, now this is a y problem. So we will say that the sum of the y forces equals 0. Okay, well, what is the sum of the y forces? Okay, so the sum of the y forces, tension is positive, and weight is negative, and that's equal to 0. All right, so therefore, this is just tension equals the weight. And that's the answer. Not so bad. So let's just review the steps. Draw the force diagram. Figure out if it's equilibrium or non-equilibrium. This was equilibrium, so the sum of the forces equals 0. And then use your force diagram to complete this equation. You know, what is the sum of the forces? Tension minus weight, and then just do the algebra. That's nice. Okay. Now, let's do a different one. I want you to do it. You can do it. So pause your video and figure it out. All right, we're back. Okay, so this one says, I mean, it's the same thing except for what's in yellow. But here it says it's moving upward at a steady speed of 5 meters per second. So steady speed, same direction. What does that mean? It means that the velocity is constant. It means that the acceleration is 0. So that's an equilibrium problem again. So basically, it's the same thing. It's exactly the same thing. Same answer, everything. Because again, the sum of the y forces is 0 because it's not accelerating. All right, let's do another one. All right, now it says that the block is accelerating upward at 5 meters per second. So obviously, this is a non-equilibrium problem. All right, so same force diagram, but just to help your brain, you know, think clearly, in my opinion, what you should do is you draw a little arrow here, label it A. That just tells your head, hey, this is accelerating up, so you don't make a silly mistake later on. All right, so now we have the sum of the y forces equals ma. If you want to put may, you can. It's really whatever. And, all right. And what's the sum of the forces? T minus, I'll say mg instead of weight. All right. What doesn't matter. All right. So therefore, what are we supposed to find? Tension. All right. So we have this equation. And so you just do the algebra. So tension equals ma sub y plus mg. Okay, well, we might as well, you know, factor out the m, save us a little work. So we have m a sub y plus g. All right, the mass is 100 kilograms. Okay, a sub y is 5 meters per second squared. G is positive 9.8. 9.8 meters per second squared. And I promise you, if you do that, you get 1,480 newtons. So there you go. All right, so that's the step. I mean, that's how you do the problem. Force diagram, ask yourself if it's equilibrium or not equilibrium. This was not equilibrium, so you have to say the sum of the forces equals ma. Then you have to use your force diagram to identify the forces, and then you just solve for whatever the question is asking for. That's it. Not so bad, right? Not so bad. Now, why did I say that the acceleration was positive 5 meters per second, not negative? Well, because it said it was accelerating upward, and we said upward was positive. So that's why it's kind of a nice idea to draw that, just to keep your brain going. All right. By the way, typically, why do we want to do all these force problems? Okay, typically, you solve these force problems like that to obtain the acceleration. That's kind of what the goal is here. It's to use the force diagrams to calculate the acceleration, and then to use that acceleration in a kinematics problem. So think of those kinematics problems that we did earlier. Well, now we're going to have kinematics problems where we don't know the acceleration, so we have to do this in order to solve for the acceleration, and then we do the kinematics problems. So I wasn't joking when I said that we're going to use everything we've learned up to this point in this chapter. All right, let's move on and talk about mass and weight and apparent weight. Mass, weight, and apparent weight, and gravity. All right, here's a question. Let's say you could take a trip to the moon, and you don't have to wear any kind of suit, just wear your regular clothes. Does your mass change? Actually, it doesn't really matter if you wear, well, it doesn't matter if you wear a suit, because I'm just asking about your mass. So does your mass change when you travel from the Earth to the moon? Just your mass, not the mass of your clothing. The answer is no, right? Because mass, you know, that's like how much matter makes up your body, right? It's a constant, you know? It's a property of the object. Okay, no kidding. Second question, does your weight change when you travel from the Earth to the moon? And the answer is yes. Well, why is that? Because weight is a force, right? It's force of gravity. So on the Earth, you know, on the Earth, we say that the weight is mg, where g is 9.8 meters per second squared. But on the moon, you know, it's still mg, but now it's the g of the moon. And g of the moon is about 1/6 of 9.8 meters per second squared. So, obviously, when you go to the moon, your weight is 1/6 what it is on the Earth. Okay? All right. Now, here, you've seen this before, this is the force of gravity between, let's just say, the moon and Earth. And so it's this big number. I mean, this small number, 6.67 times 10 minus 11 Newton meter squared per kilogram squared. So it's this tiny, tiny number g times the mass of the Earth times the mass of the moon divided by the distance between their centers. Right? That's called Newton's law of gravity. All right, so here's the question. What is the force of gravity between Earth and you? So here's the picture, right? There's you standing on the surface, and there's the center of the Earth. And so let's do it. Okay, so here's the equation. And let's just write g, let's not write the number. So the force of gravity between you and the Earth is uppercase G, mass of the Earth, mass of you, and what's the distance? Well, I mean, technically, it's the distance between the center of the Earth and the center of you, but it doesn't really matter if we go to your feet or to your center, right? I mean, this is so large. So we'll just say from here to here, which is just the radius of the Earth. So the radius of the Earth, that's the distance from the center of the Earth approximately to the center of you. So the radius of the Earth, that's an R, squared, okay? So that's, now, wait a second, what else is this? The force of gravity that Earth exerts on you, isn't that your weight? Yeah, that's your weight, right? So that's just the mass of you times good old G, okay? So that's cool. There's nothing really new there. All right. Now, what is an equation for little g? Well, let's look at it. So this equals this. I want an equation for little g. Here's a mu. Here's a mu. I can cancel. I can divide the mu's on both sides. So I divide here, and I divide here. So that is an equation for little g. Okay? And of course, that's equal to 9.8 meters per second squared. There you go. Now you know what little g is. So years ago, I mean many years ago, the scientists had a pretty good idea what uppercase G was. They had a pretty good idea what the radius of the Earth was. They had a pretty good idea for what little g was. So they used this equation to figure out the mass of the Earth. So anyway, so that's cool. All right. So in the United States, it seems that a lot of people always want to lose weight. So we have Weight Watchers and all these programs to help people lose weight. So let's say that you were very wealthy and you could just take a trip to the moon. Well, what would you do? You'd lose weight. However, would you look any differently than you did on the Earth? No, because what do we really want to lose? Do we want to lose weight or do we want to lose mass? We want to lose mass. So Weight Watchers is a poor term. It should really be called Mass Watchers. But that doesn't sound very good, so forget it. All right. Now let's talk about something called apparent weight. Apparent weight. Okay, so now what we want to talk about is the weight in an accelerated reference frame. Well, think about it. Where do you ever come in contact with an accelerated reference frame? In an elevator, right? And so think about it. You're in an elevator on the bottom floor, and it's stationary, and then all of a sudden you start going upwards. How do you feel? You feel heavier, right? Okay, now let's say you're on the top floor, stationary, and all of a sudden the elevator starts going down. How do you feel all of a sudden? You feel light. So that's this whole idea of apparent weight, okay? Apparent weight. How do you feel gravity? That's kind of a weird question, right? How do you feel gravity? You know, if you're walking around here, how do you feel gravity? Well, the normal force, right? I mean, you know, Earth is pulling down on you with a force equal to your weight, and the normal force is pushing up on you with a force equal to your weight. If you were to go up to the EA point and somebody blindfolds you and they push you off the EA point where it's safe, all right, and you don't feel any air resistance, how do you feel besides frightened? How do you feel? You don't feel any normal force, right? You feel weightless, you know? You feel weightless. Okay, so let's talk about this apparent weight thing. Okay, so here's the definition. So the apparent weight is the magnitude, so it's just going to be a number, it's not going to have a direction, is the magnitude of supporting contact forces. What? All right? So generally just the magnitude of the normal force, okay? So the magnitude of the supporting contact forces, the magnitude of the normal force. All right, so you're standing still. What is your apparent weight? Well, so pause and answer it. Okay, this should be obvious, right? If you're standing still, your apparent weight is just your weight. Okay, now, we already went through this, whatever. You are in an elevator which begins to accelerate upwards. What's your apparent weight? So pause. Okay. If it begins to accelerate upwards, you feel heavier, so your apparent weight is greater than your regular weight. And you know what the third question is? You're in an elevator which begins to accelerate downwards. What's your apparent weight? Less. All right. Now, So all I'm saying, and all you know, I mean, and you know this from your experience, when you're accelerating, your apparent weight is not equal to your weight mg. So we got to figure this out, right? We're going to use Newton's laws of motion on a force diagram to figure it out. Okay, so let's just say we're accelerating upwards. I mean, we could do it the other way, but who cares? So we're in an elevator that is accelerating upwards. So, all right. Now, what's the object? You're the object. All right. What are the forces acting on you? Well, you know, Earth is still pulling down on you, and the floor is pushing up on you. So there's a normal force, and there's a gravitational force. So let's draw the force diagram. All right. Okay, so there's the weight, and then there's normal. Normal. Okay? And the net force or the acceleration, either one, is that way, right? You're accelerating that way. All right. So this is a non-equilibrium problem because there's acceleration. So the sum of the forces. Okay, so what's the sum of the forces? Well, it's N minus W, and that's equal to ma, right? Sum of the forces equals ma. Sometimes I write sum of the forces equals ma, and then I figure out what the forces are. Sometimes I do it this way. Whatever you like is fine. Okay, now remember, okay, so let's solve for the normal force. So therefore, the normal force equals ma plus the weight. Okay, now again, oops. The apparent weight is the magnitude of the supporting contact forces. Well, for this problem, what's the supporting contact force? It's the normal force. Okay, so we're going to call this normal force the apparent weight. So apparent weight. So there it is, all right? It's equal to the regular weight, W, plus ma. Now, there's a really cool way to write this, but it takes a little bit of algebra, but it's cool. So we're going to do it, all right? So here we go. So the apparent weight, like I just said, equals the regular weight plus ma. All right, now what's the regular weight? That's mg. So we'll put mg plus ma. All right, now, in algebra, if you multiply something and you divide the same thing by the same thing, it doesn't change anything, right? So we're going to multiply, let me do a different color. We can multiply this, and you'll see why, by g divided by g. All right, so we're just multiplying by 1. We can do that. That's legal. All right, now what we're going to do is we're going to say, hey, here's a mg, and here's a mg. So we have a common factor. So we're going to factor it. So we pull out the mg, and then here we have a 1, right? mg times 1 is that. And what do we have here? Well, here's a m, here's a g, so we have what we have left is a divided by g. Okay, now, that's what we wanted to come up with. Now, why is this cool? Why do I have to do all this baloney? Because it's nice, you'll see. All right, let's check it. So let's say that we're accelerating up, all right? So we're accelerating up. So if we're accelerating up, what is the sign of A? It's positive. So A would be positive. Well, if A is positive, then this thing is positive. 1 plus this is bigger than 1, so the apparent weight is bigger than mg, right? Because, again, this is positive, that's positive, this is bigger than 1, so the apparent weight is bigger than mg, which is what we already know. Okay, let's do down. So if we're accelerating down, A is less than 0, so G is positive, A is less than 0. This is a negative number. 1 plus a negative number is less than 1, so the apparent weight is less than mg. So the apparent weight is less than mg, which agrees with our experience. And of course, 3, if we're just standing still, if we're not accelerating, A is 0, so the apparent weight is just equal to mg. No kidding, all right? So I think this is a really cool way to write it. All right. Now, how would you actually measure your apparent weight? If you're in an elevator, how are you going to measure your apparent weight? Just use a scale, right? Like a bathroom scale, you know? Just put it on the floor and it's going to measure your normal force. That's all you have to do, okay? All right. Let's talk about, you know, a minute ago or so we talked about jumping off the EA point. If you jump off the EA point, what's A? Okay, if you jump off the EA point, what is A sub y, ignoring air resistance? Well, if you jump off the EA point, you're in free fall. So A sub y equals minus g. So let's go to our wonderful equation. If A sub y is minus g, then we have a minus g over a positive g. That's equal to negative 1. 1 plus a negative 1 is 0. So what's your apparent weight? 0. All right? So your apparent weight is 0. And that's called feeling weightless. Okay? When your apparent weight is 0, you feel weightless. So here, so these are guys are, I don't know, they're out in space or somewhere, and they're in a place where they're weightless, right? They're feeling weightless. How do astronauts train for that? So this is one way they train for it. So they have this jet, and we were talking about it already. So when this undergoes parabolic motion, that's projectile motion, right? It's free fall. And so all they do is they put these poor astronauts in this jet, and they go like that. Now, most of us have been on a plane before. I mean, how do you feel when the plane is going horizontally, and then all of a sudden it drops down? I mean, really bad, right? So you can imagine how these poor people feel when they're going like this. Woo! I mean, you can imagine what they do, right? They vomit. So what is this plane called? The Vomit Comet. I didn't make that up, that's true. All right. Very good. All right, let's quit.